Without further ado, I'd like to do a little bit of an intro, if that's all right. So, Ed Conway is a writer and broadcaster. He is the economics and data editor of Sky News and the author of a number of books. Most recently, the award-winning best-selling Material World, which I have here, excellent read, an Economist and Sunday Times Book of the Year. Materials World was also shortlisted for a host of awards, including the Financial Times and Schroders Book of the Year and British Academy Prize. On a personal note, I have recommended this book both to aspiring startups and scale-ups in the sustainable design space, all the way through to C-suite leadership at multinational companies in sectors such as electronics, aerospace, and automotive. So what immediately gripped me was Ed's journalistic flair and writing a book that the layperson can enjoy reading whilst having all the citations any academic could ask for. So it's a rare blend of reality check for consumers and corporates alike, but I think it also leaves one with a sense of hope for the future. So without further ado, over to you, Ed.
Thank you. Thanks, Jude. Hello, everyone. Thank you for joining. Gosh, a really kind introduction. I've got some slides, perhaps unsurprisingly, to show, which I will do in a second. But actually, unexpectedly, one of the best things about my job. So, I'm a journalist and have been basically most of my career. And one of the best things about being a journalist is when you get invited by people or asked to go to see where people work and see what they do. And it's a true privilege to get that insight into how people's everyday lives work. I kind of feel that I feel it's a real privilege. It so happens, to some extent, the book that I wrote, Material World, kind of derived from one or a few of those experiences where I kind of find myself out reporting on stuff. And the story that I was reporting on was much less interesting than the story of here's this extraordinary plant or here's this amazing mine and here's what they do, just their everyday lives in this place that is in some way connected to all of our lives. And the reason I say all of that is not just as an introduction to this, to the book Material World, but it's also to say that it so happens. So yesterday I was at Labour Party conference in Liverpool. And today I'm now visiting an industrial site, which is not far away, where they're making certain chemicals without which I don't want to give too much away, just in case any of my rivals are listening to work out. And I don't know when we're going to air the story, but it's a place where they are producing some chemicals without which we would be in big trouble in this country, to put it lightly. And the chemical sector is going through a serious crisis now, perhaps the biggest kind of downturn, the biggest recession that we've seen in a lifetime. It is that serious. And so all of which is to say that what I'm going to talk to you about, and in the kind of following minutes, it's semi-historical, but it's also part of what we're living through right now. So let me spiel through some of these slides. You'll have to bear with me to see if I can actually get it working, because shocking as this will sound, I don't do this all the time. I just usually someone makes a kind of puts something up on a screen. I do control the screens that I do at Sky, which gives everyone a lot of kind of terror. But I hope you can see that. Do you think, Jude? Would you?
We can see that. It looks
reassure me. Yeah, thank you.
Away you go.
So normally someone else is normally this is up on a big screen. So now I'm having to do a small screen thing. So bear with me if I am a little bit more kind of stilted in my delivery. But anyway, what I wanted to talk about is some of the stories from Material World that I found interesting and to some extent inspiring, and also informative about what we're living through right now in our lives. And the first of them was, if you've read the book, you'll be familiar with this. So kind of, hopefully you won't find it too tedious to hear the story again. But the glass famine. And this is a story that goes back to, well, in some sense, it kind of goes back to the early days of glass manufacturing. But where I kind of wanted to really begin is the year is 1915. It is the middle of the First World War. And something extraordinary has happened, which is that England, which is fighting obviously war with Germany, suddenly realizes that it is running desperately short of the optical glass it needs to keep its troops supplied with binoculars. And this is really important because obviously this was the first Great War where you could really shoot your weapons further than you can actually see. So binoculars, telescopes, sniper scopes, they were all important. And Britain was running very short of them. And it turned out that most of our binoculars were having to be imported from Germany. And Germany, of course, was the country we were at war with. And this prompted one of a recurrent kind of set of navel gazing moments where people wondered, well, how on earth did it come to this? How did it come to pass that we became so reliant on another country for this life-saving technology without which lots of people wouldn't be able to fight this war? And the answer to that actually is a kind of long-winded one, which is that, oh, sorry, I missed the most exciting thing, which is that at the height of the glass famine, so basically Britain didn't have enough binoculars to go around, basically. And appeals were launched for people to donate their binoculars in. If you have a spare pair of opera glasses, if you have anything, field glasses, please donate them to these troops who are heading off to the trenches, without which they might die. And, there were newspaper appeals. The King and Queen donated 4 pairs of opera glasses. So there's this very kind of this strange, dissonant image you probably have in your heads of all of these troops heading off with gilt-edged opera glasses to the trenches. But it was that serious. We just didn't have enough of the specialized optical glass. When we talk about silicon technology these days, we've got one meaning. But back in the day, silicon technology back in 1914, 1915 was about optical glass. And it came to a head when in the middle of 1915, a British spy was actually dispatched to Switzerland to meet with his German counterparts to trade binoculars from Germany for rubber, because it turns out the Germans were short of rubber. And a lot of people at this time were wondering how, like I say, how did it come to this? And the long version of this, I'll do the kind of potted version, actually goes back many hundreds of years. Because the funny thing is, if you look back through history, hundreds of years back, it so happens that many of the times when a country was advanced in glass manufacturing, it also so happened that that was one of the great trade centers, one of the great economic centers, one of the economic superpowers of at least, the region of the world that we're talking about. So think about Venice, okay? So when Venice was an economic superpower, kind of 800 years ago or so, part of the explanation, or 700 years, part of the Venetian story was that was also where the world's greatest glass was made. So if you go to Venice these days, you can go to Murano and see the amazing glass making there. Well, Venice was one of the places where making really clear glass was really first perfected. And how was that done? That was done by taking sand from local. Actually, in the case of Venice, I don't want to go too far down the rabbit hole of sand, because that's what you can do. And that's kind of what the book is about. But in the case of Venice, actually, they found really clear, kind of pebbly bits of quartz crystal, which were in the river Ticino, I think, the river Ticino, just further north in kind of Alpine region towards Switzerland. And they took those little quartz pebbles, cogoli they were called, and then they worked out how a way of making really clear glass with them, because making glass is hard. Making glass that's clear is even harder. And the key point here you need to know is the Venetians nailed it, and they nailed it early. And because this was the great, silicon technology of its day, the Venetians didn't want to share it with other people. So they wanted to ensure that none of the craftspeople who had learned their craft of making this glass, most of whom, by the way, were kind of imported. They were immigrants, from many of them from the Middle East. But nonetheless, once they got to Murano, they were told, "You're not allowed to leave. We're keeping you here." Kind of in much the same way that silicon chip manufacturers in Taiwan are told that their employees are not allowed under any circumstances to go and work in China. Well, it was that way for Venice in the kind of 13th, 14th century. And think about it. Where you're looking now in Venice, North Italy, this was the heart of the Renaissance. And part of the explanation for that is that they had the best glass, they had the best lenses. Those lenses enabled people like Galileo to stare into space. They enabled people like Leonardo to make great art by using those lenses to create camera obscuras, because the Renaissance was not just about this amazing breakthrough in human kind of ingenuity of working out how to draw perspective. It was also about glass lenses, using glass lenses to kind of enable people to sketch. That was part of the story. Anyway, long story short, Venice was the heart of making great glass. Then it shifted gradually. Some of those cross people were smuggled out of Venice and Murano. Some of them went to the Netherlands. Some of them went to France. Incidentally, the Netherlands. It is not coincidental, by the way, that the golden age of Dutch painting happened around the same time that the Dutch became incredibly good at making glass. Why is that? Because glass lenses were really important for making amazing art, because artists used lenses to for camera obscuras, which they then enabled them to make extraordinary works of art. Then it shifted across to France. And then gradually it found its way up to England, and there were cross people that went there. And so the long story about how Britain kind of ended up needing to rely on Germany for its binoculars is that actually we were really good at making lenses. Some of the great advances in making kind of crown glass, certain types of lenses happened in England in the kind of 17th, 18th centuries. But then, as often happens, the government realized, oh, hang on, there's a cash cow here. We need to make some money. And what they did was they taxed it. And so you had a variety of different taxes. You had the window tax. And the reason I've got a picture of the kind of old kind of Georgian building there with bricked up windows is when the government decided it was going to start taxing people on the basis of how much glass they had in their houses, people naturally just bricked up their windows. So you had the window tax. You had glass duties, which basically made it really unattractive for people making glass to manufacture this stuff. And again, long story short, gradually the glass industry, which was massive in England, kind of withered away slightly. And slowly but surely, a lot of the focus, a lot of the investment shifted to Germany. And in Germany, while the UK was kind of trying to, or Britain rather, was trying to just make money out of its glass industry, in Germany, they were really trying to invest in their industry. And you had, in a sense, the kind of early stages of industrial strategy, building up a glass industry, which resulted in, well, these two people. These were two of the great forefathers of glass manufacturing. Otto Schott, who was kind of the guy who pioneered a lot of the early manufacturing processes for making glass, and Carl Zeiss. And obviously, you'll recognize the name Zeiss because, it's Zeiss. That's where the lenses come from. That's where the binoculars come from. And those are exactly the binoculars that Britain had run short of in the glass famine. And so part of the reason why the UK, or Britain rather, didn't have the binoculars it needed at that point was because it had allowed its industry to wither away. And the funny thing is actually, when I was kind of going through the archives to try to understand, because like I say, not many people talk about the glass famine right now for understandable reasons. But I went into the archives and looked, and there were all sorts of documents about how on earth did we allow such a disaster to happen, where this important material that we used to keep ourselves alive within this war suddenly wasn't there anymore. And there were all sorts of kind of assessments about what went wrong. This is one of them. And you can see the quote I've highlighted there. It says it paid the trade better to act as middlemen for the Germans than to manufacture. And the reason I kind of mention all of this is because I think there are lessons to be learned, these days. The most striking thing about the spy going off to do a deal with the Germans is not just the fact that they went off and did it. It's the fact that actually the Germans said yes to doing the deal. So you have this extraordinary situation in 1915 where the Germans are willing and the British are willing to trade each other with these crucial ingredients. The Germans needed rubber for fan belts and other kind of tires and things like that. So they both needed these products to try and kill each other, basically. And they were willing to do the trade, which is kind of ghastly. But the other interesting kind of takeaway from that period, and this is where you'll see the kind of relevance of this later on, is that this is just showing this chart. I love charts, by the way. So, this may not be the last one you're going to see, I'm afraid. But there aren't too many. And Jude's going to kind of stop me at some point when I kind of go too charty. So this is showing you how many the imports of glass to the UK in this period of kind of 1912 to 1918. And look at the green bits. That's imports from Germany. And what do you see there? You see that we, in the kind of quarters up till 1914, about 60% of glass, optical glass that we needed for these binoculars came from Germany. And then, of course, the war breaks out. So the green bits are going to go away. But here's what's really interesting, okay? Look at what actually happened next, okay? Look at this. So look at the white bits. The white bits are showing you British production. And British production, which was really low before 1914, suddenly gets really high. And what's that showing you? It's showing you that in the event of a war, of something terrible happening, then you can potentially reindustrialize. And I'll come back to why that's interesting in a bit. But that's the story of the glass famine from 1915, and it's one of the stories. If you've read Material World, then you'll probably have read that bit. And it's kind of early on in the book. The point behind Material World, really, like I say, it was partly about going to sites and seeing places and thinking, God, this is amazing. I wish I could write more about this. It's partly about understanding what are the things that we need to make the world kind of work. It was partly, this, I guess, a moment of revelation when I was standing on the lip of a gold mine thinking to myself, golly, well, I hadn't quite realized that this is what it takes to mine gold. And I'm a part of this, I just got married. I haven't, bought my wife an engagement ring. I was kind of thinking to myself, well, that's probably where this gold came from. And if it takes the scale of destruction it takes to mine these days kind of beggars belief. There was a whole mountain basically being destroyed in front of me. I'll show you, there's a picture of it later on. But it struck me, well, what is it if this is the amount of destruction it takes to get something that's relatively discretionary like gold, what is it that it takes to get the stuff that we really need to stay alive? And that's kind of part of the backstory of Material World. But part of it was something else. It was kind of, I remember, I don't know, if any of you studied economics, one of my favorite essays from early on in economics was this one called iPencil. And the idea behind iPencil, kind of, this is an adjoined point to the previous one, is to say a pencil seems like the most simple thing in the world, doesn't it? When you look at it, it's kind of, only a few parts to it. But actually, when you think about how a pencil is made and the processes it takes to get it, it is a very complex supply chain. It takes, you've got people chopping down the trees in one part of the world for the wood. You've got people that are mining the graphite that's going into the lead. You've got people that are getting the rubber that's going into the eraser. You've got, look at that metal bit. You need people who are getting metal out of the ground, steel, zinc sometimes, putting it into that. And when you think about the number of people who are involved directly or indirectly in the supply chain, actually, it is a lot of people and it's a lot of different expertises. And there is no single point. This is the point that Leonard Breed makes. And it's iPencil because it's like, me as a pencil, this is what I'm telling you, my family tree, my story. But the point is, there is no single person who knows how to make a pencil, which when you kind of take a step back and think about it, it's kind of amazing, isn't it? And I remember reading this essay back when I didn't do economics at university, for better or for worse. And I did kind of later on go and do a master's, which kind of covered a lot of economics, but I didn't do it. And so I kind of found myself kind of teaching myself economics when I was in my 20s, I guess. And I remember reading this essay and thinking, this is just so interesting. And I wish there were more stories like this. I wish there were more kind of iPencils about all sorts of different products. Because I'd just like to know how stuff is made. And I think it tells you something really instructive about human ingenuity and interaction. And so, long story short, one of the things I always wanted to do in Material World was to try and do a few iPencils, so for various different things. And I kind of did it for batteries, and there's a few other bits and pieces in there. But the one that I did that I was kind of determined to do, partly because it was like the hardest of all, was this one. So silicon chips. Can you tell the kind of story from ground, from earth, from mine to finished product of silicon chips? That's the kind of task I set myself. And by doing that, what do you learn? What do you learn about the challenges in, providing these products that we all come to depend on, that are in all of our products, that we are able to communicate? You're able to watch this thanks to what you can see there. Transistors, silicon chips, a chip that contains billions of transistors on it. Transistors that are so small that they are smaller than the wavelength of visible light. Mind-blowingly small. Literally, they're so small they are invisible. Humankind makes that on a day-to-day basis. But how? And so that was the kind of road I wanted to go down, and do the iPencil on silicon chips. And by the way, if you understand how a silicon chip is made from mine to finished products, then you also understand how solar panels are made, because solar panels are basically kind of the same as silicon chips. It's a cruder, slightly cruder finished product, but you basically have to do all of the same industrial steps for kind of from mine to towards the end of that supply chain. And what do you learn? Well, you learn, by the way, um, when I embarked down this kind of road, I spent quite a lot of time, because I'm a journalist, I spent a lot of time talking to people who work within chip production. And very few people were able to answer the question, where does the silicon in a silicon chip come from? I'd be talking to people who were kind of like senior people at some of, household name, well, maybe not household name, but chip fabs and producers who are producing the silicon chips we all depend on. And I'd say, well, they'd start to talk to me about the lithographic processes, which we'll talk about in a second. And I'd be like, well, that's all very interesting, obviously. But where does the silicon come from? And they'd be like, I mean, it's just sand. Like, honestly, Ed, who cares? And I'd be like, I care. And I think, maybe some other people do. I hope so. Um, and again, it's that iPencil thing. No one who's at the end of the supply chain is thinking, you know, all that deeply about the other end of the supply chain as a matter of course, because they get their inputs and they just do their job. And then that's hard enough without having to try and think of everything. So what is this journey that the silicon chip goes on? And like I say, it's the same for solar panels. And if you're interested in sustainability, I think this is pretty eye-opening as well. It certainly was for me, because when I'm thinking about solar panels, I'm not really thinking about kind of explosions and carbon emissions and other things. But nonetheless, it's part of it, because every single thing we take out of the ground involves a bit of energy to turn it around and turn it into a different product. And that's definitely the case for these things, as you will see in a moment when I have another chart, if I'm allowed to put it up, which is, anyway, things before we get to that though, okay? So let's start with where the silicon comes out of the ground. I wanted to go to physically touch what would later become a silicon chip and a solar panel. And it turns out it's from places like this. So this is a quartz mine in the north of Spain, Serrabal it's known as. And you can see there it's nice and white. This is pretty high quality quartz. And what happens is it's blasted out of the ground. You've got big explosions here. You can see this was kind of a hill. There's a big gap in the middle of it. And those explosions there, blasted out, and it kind of comes out in fist-sized chunks. And those fist-sized chunks are then put into a truck, and they're driven along to another plant. And in that plant, it goes into, it's kind of like an electric arc furnace. And you see it there. If you've seen a steel plant, like an electric arc furnace steel plant, making silicon chips is basically the same as making steel. At least the very first stage of metallurgical process. It's kind of like making steel. And so you chuck all of your fist-sized lumps of quartzite, as it's known, into that pot. You put wood chips, you put coal, coking coal in there. This, by the way, is the process of making silicon chips and solar panels. It uses coal because you need some way to get the oxygen off that quartz so that you have nearly pure silicon. And there is no better way that we've discovered so far, and hope, potentially we will in the future, of getting that off than using coal in this process. And so then that happens. It's a pretty, as you can see, it's like being kind of in the mines of Moria. It is dark ages in there. And that is the start. That's the start of how you make silicon chips and how you make solar panels. But what happens at the end of this is that all of the stuff that's kind of spurting, kind of coming out of the container, it's about 99.9% pure, maybe 99.8% pure, which sounds pretty pure to us, but it's not pure enough. Because if you're making silicon chips that are going to have tiny, tiny transistors, you need to make it even purer. So what you do is you take that silicon and then you kind of break it down chemically through something called the Siemens process, which results in what look like these kind of filaments, things you see on the bottom of a kettle. These are not things you find on the bottom of a kettle. This is what's known as polysilicon. And what all polysilicon is basically even purer silicon. So you've taken your 99.8% pure and you've broken it down in this kind of almost atom by atom, and you end up with what you can see there, which is 99.9999999, possibly another 9% pure silicon. It's 9 nines, they sometimes say, 10 nines. I think there's even kind of 11 nines. And what that means is basically it is one of the purest things that humankind is capable of making. But even that is not good enough, because although it's pure, the atoms aren't quite in the right places. So what you need to do is you need to break it down again and find a way of reconstituting the atoms so they are in a perfect matrix, a crystalline structure that is what's known as a monocrystal rather than a polycrystal. That's why it's polysilicon. This is going to be monocrystalline. And to do that, you need to break it down again. You need to melt it in a crucible and then reform it using something called the Cherkassky process. And then at the very end of that, you have what's known as a silicon wafer, which is the kind of round little thing. The round thing, it's kind of a pizza size thing. As you can see, there's two different sizes here. It's kind of 12-inch pizza, and the bigger, I think it's maybe 12-inch and then smaller, I think 8-inch. And so those are the things that you see there. When they are sliced up into incredibly thin little slices, that is what you then send to your fabrication plant, the TSMC, places like that, where it will go into a machine like this. So this is known as an EUV photolithography machine. And what's happening in here basically, it's made by a company called ASML. And what's happening in here, you see those kind of purple bits right in the middle. That's beams of light, which are bounced off various different lasers, so the way the photolithography is kind of done is, think of a cinema camera. You're taking a small image and you're blowing it up to a big size so that it can fill a cinema screen. With photolithography, you're taking a big image, or in this case, it's not really big. It's like kind of maybe the size of the laptop screen you're looking at right now. And you're using lenses to blow it down into tiny, 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 almost beyond belief dimensions. Because the whole point of making silicon chips with tiny transistors is you're working at micron breadth. And in order to do that, you're using light to do it. And the extraordinary, mind-blowing thing about these particular machines is the kind of light they use to do it, with the kind of light that doesn't even exist in the wild. It's called EUV, extreme ultraviolet. And in order to create that extreme ultraviolet, you need to take molten tin and blast it with 3 lasers, just to generate a little bat squeak of EUV light, which you then bounce off those lasers you can see there. You see those lasers that are kind of all around there. Each of those, sorry, not the lasers are bouncing off mirrors. So all the purple stuff is bouncing off these mirrors. Each of those mirrors, okay, is so perfectly flat that if you were to expand them to the size of the continental United States, I think the biggest deviation is, I think it's less than a millimeter. If you just kind of like think about that for a second.
Ed, you asked for a quick time check, 10 minutes.
Okay, yeah.
Make your flow, carry on.
I'm blathering on. I mean, but that's the risk. Each of those mirrors is basically the flattest thing that humankind has ever made. They are bouncing light that is going down to the most perfect thing that humankind has ever made, which it mass produced, which is the silicon wafer, whose production you saw a moment ago. And who do you think makes those mirrors, the most flat mirrors that we in the world? These ones. Who's the company that makes those? It is none other. And you can see, by the way, if you look on the bottom kind of left, you see where the, can I annotate? Can I even make this work? Oh, hello. That's where the silicon wafer is. Who makes this these mirrors? It's Zeiss. So it's the same company that we saw that was making the binoculars back in Germany, 100 years ago, which Britain needed to send spies to Switzerland to do a deal. And what you kind of, I think this underlines is a few things. First of all, there are pinch points. Oh, can I get rid of that thing? That's the question, isn't it? There we go. Clear all drawings. There are pinch points everywhere. So ASML is the only company in the world on the left. They're the only company in the world who are able to make that machine that enables you to make the transistors small enough that your iPhone works. If you have an iPhone, if you have an Apple computer, if you have a smartphone these days, a Samsung, that is made in a machine like that. It is made with lenses made by Zeiss in a machine like that. And along the way, I talked about the Czochralski process, where you're having to melt down the polysilicon so you can reform it into something perfect. That has to be formed in certain containers, crucibles, that are made out of a type of sand that is only found in one place in the world, which is spruce pine in North Carolina. Now, these are just three examples of pinch points along the silicon chip road, but there are loads more. And it just underlines how fragile the world is. I think lesson number two, the world depends, even though silicon chips are an incredibly new technology, think about some of those processes you've just seen, without which you couldn't have silicon chips. It depends on really old processes. So you've got the Czochralski process, which is just over 100 years. You've got the Siemens process, which is kind of, getting on for 75 years old. You've got electric arc furnaces, which go back to the 19th century. We are still dependent right now for the newest technology in the world on some of the oldest technologies in the world. All of which is to say, and I'll just whiz through a few pictures, is on this journey. And like I said, I mentioned earlier the gold mine I went to. This is the place. This is the Cortez gold mine. I took this photo. And it's basically showing you just the extent to which the mountainscape has just been scraped away so we can have gold. This is one of many different industrial environments around the world. You could look at, for instance, the salt flats where lithium comes out of the ground in Chile, the Atacama Desert. You could look, for instance, at places that copper, for instance, comes from. It is Chuquicamata. It is the world's biggest man-made hole. They're very proud of that. They vie with another mine, another copper mine, actually, in the US, Bingham Canyon. But they think they're bigger, they're deeper. It's like the Grand Canyon, but that is human-made, and it is mind-blowingly deep. It is so deep, by the way, that it's kind of got a microclimate at the bottom. It's so deep that the amount of stuff that they are kind of pulling out of the earth doesn't really have anywhere to go to. So there's a nearby town, the town of Chuquicamata, which has been buried and is continuing to be buried by the waste rock from the mine. I mean, look at that picture. It's kind of extraordinary, isn't it? You see those they're called tortas, like a kind of cake. These big, almost mountains of waste rock. Well, this is part of the reality of how we get stuff out of the ground and turn it into products that we use every day. And we are all part of this story. I'm going to give you, am I allowed to just do two charts, Jude, which will then round it up? I'm honestly like, exactly, because I've got about another 9 charts that no one's going to get to see, which is tantalizing, isn't it? But there we are. So be it. This is just a striking one, okay? Because if you follow sustainability, you've no doubt thought about things like steel and concrete and the fact that they have lots of carbon emissions. And this is one of the biggest challenges facing us as we move towards net zero. But I just think we often don't think about the other stuff. And mining is really carbon intensive, and steel production is carbon intensive, and concrete production is carbon intensive, but so also is silicon production. So this is just showing you the carbon emissions from silicon are greater per ton of end product, considerably greater, like almost 10 times greater than the carbon emissions of steel. And how much are we talking about silicon production? Not much. But this is how solar panels are made, and it's how silicon chips are made. Now, admittedly, it's in much smaller quantities. But nonetheless, it ought to be part of the conversation, but it isn't much. And the final thing I'm going to show you, this is kind of making a slightly different point, but I think this brings us back to kind of where we are today. Think back. Oh, there we are. Silicon production more carbon intensive than still. Think back to that chart I showed you earlier, which showed you the imports of glass, optical glass, binoculars from Germany to Britain back in 1914. It was about 60%. Okay. we were fretting back then, or at least we were, when we went to war, about the fact that we were so dependent on a single country for something so important. And how could we get ourselves into that position? And how could we ensure we never found ourselves in that position again? Okay, so that's Germany, that green thing. I want to now show you a few other things like polysilicon, which is where you get silicon chips from, lithium, copper, cobalt, cement, and look at where the majority of global production is actually happening. And look at the extent to which those red bars are, in some cases, look at solar wafers, look at offshore turbine blades, look at EV batteries. The red bars are bigger. Our dependence is bigger now on China than it was on Germany back in 1914. And I don't know what the lesson from that is, whether it means that we're in a better position because we're also enmeshed with each other, or whether it's a dangerous position to be in. But nonetheless, when you hear leaders around the world, it's, including Keir Starmer, but including Donald Trump, say we need more domestic production, they're often thinking about charts like this. Well, they're probably not thinking in charts, are they? But they're because that's, who does that? But they're thinking about dependence. And what we don't talk about enough is where stuff comes from and how it gets there. And when you go, final thought, and then love to do questions. When you go down the rabbit holes of thinking where stuff comes from, I find it really enlightening, because when you do that, then all of a sudden you're thinking about charts like this, and you're thinking about the compromises, the environmental compromises it takes. That should now no longer be the screen. The environmental compromises it takes. You're thinking about the human rights compromises it takes. But you're also thinking about something amazing, which is back to iPencil, which is we do this stuff on a daily basis. And we take rocks and we turn them into microchips with transistors that are so small that they are invisible. And somehow we do it. And I find that kind of truly amazing and quite life affirming as well. And final thing, what are humans like ultimately? We are a species that are very good. I mean, we're defined by it, really. We take stuff out of the ground and we turn it into tools that improve our standard of living. I imagine many of you are involved in that and designing and thinking about that. Today, and we did that in the prehistoric era. We're doing that in the Neolithic era. We took rocks out of the ground. We took rocks out of the ground and we fashioned them. We knapped them into flint axes, and they improved our standard of living. Today, we take rocks out of the ground. We fashion them in the machines you've just seen into silicon chips, and they improve our standard of living. Well, they also kind of let us do doom scrolling on social media, but they, to some extent, improve our standard of living. We are still living in a material world. We still need the stuff. We still need to get it out of the ground. We still need to turn it into products. We just kind of sometimes, a lot of us have forgotten about that. And I had until I started kind of going deep into the rabbit holes. And then you go in the rabbit holes and you're like, wow. So anyway, that's my spiel. I'm sorry I went on so long, Jude, but
No, it's perfect
there we
timing,
are.
actually. That was great.
There we are.
Thanks so much.
Who knew?
Yeah, I thought there was one thing that I know we discussed previously. I wondered whether you could expand a little bit on the Jevons paradox. And obviously you'll explain it more succinctly than I am, but I thought, given that the audience is a mixture of, design, engineering, industry, I thought that was somewhat a cautionary tale. So would you care to elaborate?
Am I allowed to show a chart in my response to this question?
Of course, we'll let it.
I do actually have one. Jevons. So basically, there was this guy, William Stanley Jevons, who was an economist in the kind of 19th century. And the point he made, okay, is that the more coal we were mining, basically, even though we were getting better and better at kind of making machines that were even more efficient with taking coal out of the ground and turning it into motion, so draining mines and making kind of steam engines and things, the steam engine was getting better and better, in theory, you would have thought from that we'd be using less coal because the steam engines are getting more efficient. But in practice, we were just consuming more stuff. And I think about that quite a bit because this is a chart. Okay, this is the most hopeful chart in the world. Okay, which is showing you where people thought the solar PV net addition, so basically how much solar panels there are in the world, would be, and where it's actually gone. So isn't that amazing? Our appetite for solar panels has kind of gone up, has gone through the roof. And in theory, you look at that chart and you're like, this is great because we are making progress towards net zero, which we are. But then you kind of have to look at the flip side of this, which is to say that most of those solar panels, okay, are made in China. And if you look at, and they're made, you've seen the process not that long ago about how solar panels are actually manufactured. It's quite energy intensive. You do actually need coal for it. You need a lot of power for it because the electric arc furnaces are mostly power. So you need the coal, the physical coal for the chemical process going on inside that tub that you saw, the vessel. And then you also need the electrical power to create a lightning storm inside it, which is what an electric arc furnace basically is. China is burning crazy amounts of coal. And every single year, forecasters think that that's going to flatten just the same way that they thought solar panel output was going to flatten. But in fact, Chinese coal consumption goes up. And actually, since I made this chart a year or two ago, it's kind of gone up even further. And all of this is to say, we tend to, when we consume, see now I'm on my charts, but I'm sorry, Jude, I'm going to do it. You can't stop me at this point.
Don't worry, there's two people you've clearly paid to
it's
say
relevant.
the charts.
It's relevant to this, though. It is relevant to the point about the Jevons paradox, which is to say, we as a species, as well as being having an amazing kind of propensity to take stuff out of the ground and turn it into products which improve our living standards, we like consuming stuff. And the paradox of something like the energy transition. So you've probably seen charts a bit like this before. When we talk about the energy transition, there's the sense that, look, this is great because we are going to shift. We're going to shift from the wood age to the coal age. And then we're currently in this kind of oil and gas age. And that's going to be followed by this kind of renewables era. And when you look at the charts like that, it kind of does look quite encouraging, doesn't it? Because look, wood went away and coal went away for the most part. And, oil and gas might well go away as well. But what you've got to remember about this is look at the left-hand axis. This is your share of useful energy. It's not the total, it's the share. Now look at the same data. I'm going to show you exactly the same data, but different perspective. And this next one is just showing you the total amount. I think it's in terawatt hours, where the energy comes from. It's exactly the same data. It doesn't have the kind of future projection bit, but it's exactly the same data. And what do you see? We're not transitioning, we're layering. So the consumption of certain things doesn't actually go down. It's just other stuff gets on top of it. And Jevons's concern, I think, was that we would always have this demand to just consume more stuff. And I'll stop there because otherwise it's ridiculous, isn't it? We have this demand to consume more stuff. And that, the example I sometimes give that's pretty kind of topical is LEDs. So when LEDs were invented, everyone was very, rightly kind of excited that we have this amazing new technology which enables us to have light with far less energy consumption and also far cheaper. And the three Japanese inventors of blue LEDs, which was the kind of final technology that got us to white LEDs, they got the Nobel Prize. And part of the kind of citation for the Nobel Prize was, this is fantastic because it's part of the solution to the energy crisis. Well, it is, if you believe one thing, which is that our total consumption of LED of light is going to go down. But instead, actually, rather than banking all of those savings, we just do more stuff. So look out, Christmas is coming up soon, and you'll see all of those. Every local park has a Christmas spooky. It's Halloween. There's a spooky trail, and then Christmas, it's one of those things. It's all LEDs. Look at the Sphere in Las Vegas. It's all LEDs. Look at the headlights on a typical car. This is a really good example. There used to be halogen. There was one headlight in there, basically. Now, matrix LED headlights have potentially a greater energy consumption than those previous headlights because there are so many individual LEDs in them. And so the Jevons paradox is to say, even though we're getting better and better at kind of making things more efficient, is there this inbuilt something in human propensity that means that there will be some unpredictable reason why in future actually our energy consumption goes up rather than down? And I think that's kind of plausible, and it's hard to disprove in history. Anyway, sorry, really long answer. I promise not to do any more charts.
No, that's great. And I tell you what, I'll do a two for one question. That way you can get into your stride. So this is from first N Castle and John Williamson. So obviously, thanks for the presentation. Interesting to see any links between possible contradictions between short-term viability and long-term security. So the question is, what do you see for the UK government enabling the transition from circular economy related to the UK task force on circularity? And just as a quick follow-on from that, what do you believe in terms of localizing means of production manufacture essential for circularity? But the common rebuttal is that localizing, you reduce things like buying power and efficiency.
Mm, really good questions. I think the paradox, it comes back, this all comes back to something else, doesn't it? Okay. It comes back to the fact that the way that the economy has been structured for the last, at least the last kind of 50 years or so, has been predicated on price. It's been primarily about how do we bring prices down so much that it improves living standards more broadly. So it has a very virtuous ambition. And sometimes the answer to that is basically, rather than making stuff, why wouldn't you just buy it? If some other factory on the other side of the world is making stuff and it's cheaper, then why wouldn't you buy it from elsewhere? And the benign consequence of that is things get cheaper. But the malign side of it is that you lose your ability to control any of the downsides of that, whether it's environmental downsides or whether it's human rights downsides. And if you buy a solar panel from China, it is really cheap. They are incredibly cheap now. You can buy solar panels that are so cheap that people are using them as like fences. It's mind-boggling, and that's partly because of economies of scale, but it's partly because when you buy a solar panel from China, the environmental standards are much lower than buying it from Europe and US, to the extent that you still can buy solar panels there. The effluent from those mining processes I've shown you a moment ago, that's just a lot of that just goes off into local rivers, which you can't do here, making it more expensive to do this stuff over here. The power plants are coal, which again, we have fewer of those, but it's cheaper. And the problem is, it's very difficult to fight. I mean, that's what I kind of have tended to experience. Talk to people in the Treasury here in the UK. They're very, very, very laser focused on price, understandably, because they want people to be able to have cheaper stuff. But the question, I guess, is are there some areas where that price isn't a true reflection of either value or impact? And I think that is a reasonable question. It's a reasonable question that economics hasn't been very good at confronting thus far, and policy hasn't been very good at confronting thus far.
So maybe this is a useful just provocation from Sharon here. Thanks for an interesting research and story. From an ecology viewpoint, it's extremely important to situate that the I-Pencil essay with a liberal market economics that it adopts and promotes, and which has created the ecological problems that we're now trying to fix. So I was wondering what your response is to Sharon's provocation.
Yeah, no, I mean, I think it's a good question. And I mean, the flip. The funny thing about that essay, which was always to me the less interesting thing, but I guess because I'm slightly post Cold War, is that when it was written, it was all about, listen, central planning is can never work. That was the argument, and Milton Friedman fixated on that essay because it was like, here's a really good example of why central planners can't work, because no one knows how to make a pencil. So how can someone, in Gosplan, determine the manufacture of I don't know, all of the kind of tractors in Soviet Russia? that was the kind of argument. Um, so I think that's it's definitely an important proviso. As for whether it is primarily the liberal market economy that is responsible for where we are now, I don't know if I buy that, because I look at China, I look at kind of Soviet Union during that period. Um, would those production methods have been cleaner for the global economy and prevented the what we're seeing with carbon emissions? I'm not entirely convinced. Look at China right now, and it's I guess a somewhat less liberal market system, and China is, well, in some senses, it's producing a lot of the stuff which will be the solution to the energy kind of transition right now. The solar panels. Thank God the solar panels are so cheap. But like I say, the flip side of that is, because we typically are not scrutinizing stuff as much because it's happening outside of our borders, what are the downsides that we're not sure of when it comes to solar panel production? So I think, you know, I think the thing that I wrangle with is that all of this makes me uncomfortable. I think all of this should make all of us uncomfortable, not just because there is this massive crisis that we're facing, not just because looking at carbon emissions, they are very high, and we're seeing kind of climate change in its various guises, but because we're all a part of this. We all consume stuff. We all, we may not think about it when you're kind of, I don't know, kind of consuming anything, but for the most part, that takes quite a lot of chemicals going into it. It takes quite a lot of mining. It's very hard to live a truly footprint-free life these days. And I agonize over that. But by the same token, it's thanks to things like artificial fertilizer, which comes from natural gas, that we're able to support 8 billion people in the world. Half of us would be dead without it. And I think that's something that should give us pause for thought.
Absolutely. And I think, it's one of those, words that I've sort of heard getting used more and more, of externalities, the bigger picture and the consequences of what you do, which I think maybe might lead into a nice segue into Justine's question, of great to hear your hinting of how overconsumption fuels over extraction. During your research, did you come across or engage with any indigenous leaders who are trying to protect the land as kin, rather as a resource to be extracted? Any examples of how they're engaging with industry?
I met quite a lot of indigenous kind of leaders and people in various of the places I went to. The first mine you saw, well, not the first mine you saw, but the first one I visited, with the Cortez gold mine, it is literally being dug into a sacred mountain that's for the local Western Shoshone tribe, Native American tribe. The lithium salt flats in Atacama, again, indigenous people locally, many of whom resent the presence of the lithium miners there. The tricky thing is, for a lot of these people, that is the that is a source of income. And so when you talk to kind of some of these people, it's very few of them actually want it to go away and want to do it differently. It's for the most part, and that might just be a selection thing. I mean, I did talk to a few people that were in overlooking the Atacama, who want no part of it. But they are, I think, mostly outnumbered by people within their kind of local communities who see that there are jobs and who see that there are kind of mining royalties that tend to find their way into their communities. Where that ends, whether it ends in a happy way or not, that's, there's not a great record on that. And I do think miners have got better at that, but I think there's historically a terrible record. And if you look at pretty much any kind of rich resource of any metal or mineral out there, the striking thing is often it happens to be on indigenous land, that it's sometimes that's held sacred by local communities. And it's very hard to find somewhere that doesn't involve kind of rupturing some of those old things. I mean, one of the chapters in the book is a whole chapter on what happened in the Pilbara with an incredible old, well, it could have been a monument, this set of caves, Juukan Gorge caves, that were blasted by Rio Tinto, who at the time were kind of seen as one of the better miners and better, in terms of their engagement with local communities. They still blasted these mines, which have some of the remnants
Hmm.
of some of the oldest continuous civilization in the planet. So anyway, yeah, it's tricky, and again, it's another one of those things that's discomforting.
It was, yeah, it's a very moving chapter in your book, and I would urge anyone to sort of, dive into that. I'm going to try and fold in a question from Holly and Sophie together. Of firstly, what is the situation on recycling silicon? Is there any processes? And also just a reflection that as things get cheaper and more disposal, have you been to any e-waste facilities that are full of those tiny chips? What is basically the outcome of that? I'm just conscious of time. Forgive me
Yeah.
for
I'll,
truncating.
I'll, I'll try and be quicker. I'm sorry. Yeah, I went to a few. I think recycling is hopefully the sexy future for mining. If you think about kind of ore, when mining, big rocks of chunks of copper ore when they come out of the ground, you know so much of our waste is ore, and we need to get better at processing it. We need to get better at sorting it. Silicon is an interesting one. I haven't thought deeply about specifically silicon recycling. I sincerely doubt that they do much of it, frankly, because there's not much of a shortage of silicon. The silicon itself, I mean, yes, there's certain varieties which there's not that much of, but I don't think they do that much recycling of silicon. And it's a good question. I don't know whether it's probably quite difficult because the finished silicon chip is actually not just silicon. You've got a whole load. It's like a cocktail of different actual elements by the end of it, and probably it's quite hard. The hard thing about recycling is separating one bit from another. It's kind of seems basic, but actually it's really important. But it's a good question, and it should be where it's at in the future. The question is whether we can set up the incentives so there's enough price and you make enough money out of recycling.
I honestly, I do want to ask questions about China and all sorts of other things, but it's just, we just don't have time. But obviously, thank you so much for being with us here today, Ed. And I guess just for the audience, please do pick up on LinkedIn, indeed, if there's any other questions. But it's really been, so inspiring to have what is a tour de force of just one small segment, but then expanding that to a bigger philosophy that I think demands closer inspection, whether we are consumers or producers, as of course we're all still consuming. Any
Correct.
other final thoughts, Ed, before we go that you wanted to raise or bring to people's attention?
No, not no. I mean, just to say thank you. Sorry, I banged on a bit. Sorry, I showed too many charts. Like the world is a more is so much more deeply fascinating the deeper you look into it, and that's kind of the one thing. What I've tended to do in this last few years is just try to start with something that seems simple and then burrow into it. And the more you burrow into it, the more you see a way of seeing the world that can change your life. And if you think more about the items and the products that surround you, and if you understand the journey they've been on to get to you, then I think you start to respect them more and you start to treat them in a less disposable way. And you start to realize that they have their own history before they get to you. And that is a kind of more functional, I think, relationship with the planet than the one that we have at the moment. And it doesn't have to be rooted in ideology or anything like that. It's just rooted in we're a people that live on this planet. We cohabit with all of the materials and the other creatures around us. Let's just think a bit more about where stuff comes from, and by doing that, hopefully, gradually kind of change our way of living.
Thank you, Ed. What a real and inspiring ending to a great talk. And thanks for all the participants and the great questions we've had. Please do enjoy the next one as well, which will be in a month or so.